you. Thank you for the introduction. Thank you for coming. And I hope I won't bore you too much in the next 45 minutes or so. I will give this presentation in English, but if you want to ask questions afterwards in German, that's fine. Also ich werde die Präsentation auf Englisch geben, aber ihr könnt gerne nachher auch auf Deutsch Fragen stellen. Good. And otherwise, you can also come up to our stand if it's not flooded right like now. So, let's get started. I'm a bit excited about the next slide. I've tried to show this a couple of times and it never worked really, so we'll see. Okay, the sound is missing. Now you have to imagine there's a loud roar coming, and it gets louder and louder, and even louder, and now it's really loud, everything's vibrating, and now it's gone. Shall we try it again? Now I still see it, and it's sort of hanging mid-air. I don't know how much longer the rocket can be there. Otherwise, it's not so important. It's just a little introduction to get you familiarized with space. Just, we can go back to the normal presentation, that's fine. Basically, what this is, or was the launch of our latest satellite. It's already nearly 2.5 years ago. It's called MTGI, where this stands for METEOSAT Third Generation, the Imager. And this is the image. That's an image from this imager. And I'll run you through a little bit of things, what we are doing in space or Earth observation. And, well, who's we? We, in this case, is EUMETSAT. We operate the European weather satellites. We have our headquarters in Darmstadt, which is, depending where you come from, far or not too far from here. We have 30 member states, which are here in blue and green. And we have 10 active satellites, which is quite an achievement considering we are like 40 years old now, nearly, and where we started off with one satellite. That's quite a growth. This is just some images from our premises. We have all the member states' flags. We have a nice pond in the shape of Africa, because that's actually what we mainly see with our satellite, just Africa. It's right in the middle. That's a view of the control room. We have a nice presentation room at EUMETSAT where you can look into the control room and see how the people work there, or don't. I've been told that the less they do, the better it is. So we have 10 satellites. We have something that's called METOP. We have BMC. We've retired A couple of years ago. So that will slowly come down to Earth and burn up at some time. It's hard life as a satellite. So first you are put on top of a rocket and they ignite all this very explosive liquid underneath you. Then they shoot you up into space, and then you're left there alone, and then either you're pushed out further, or they burn you up. So, then we've got some others. They've called Sentinel-3, and then we've got a Sentinel-6, which is measuring ocean surface topography, wave heights, and ocean heights. We've got the METEOSATs, which are geostationary. And we've got a new one, and we've got one over the Indian Ocean. So we're covering quite a bit of the Earth with our satellites. And we have to do some physics, I'm sorry. So it won't be too bad. We have two things I want to cover with you. One is orbits, because I'll be talking about LEO and GEO orbits, and I want you just to understand what the difference is. It's not too difficult. And I want to show you a little bit about the electromagnetic spectrum, what we can see, what we cannot see, but what the satellites can see. So geostationary orbit is maybe the one you are most familiar with if you have a satellite dish and receive television programs. So this satellite dish would be looking at a satellite in geostationary orbit. That means the satellite is always at the same place. From you looking at it, and also from the satellite looking down to Earth. It is at a height of about 36,000 kilometers, and it's not stationary. It has an orbit like every satellite, but this orbit is exactly 24 hours. So it revolves around the Earth at the same time as the Earth revolves. We can cover about plus minus 65 degrees from this viewpoint of the satellite, and you see this in these rings up here. That's just basically the areas we can cover with a geostationary satellite. We see a little bit more, but then it gets dodgy. So you already see towards the poles, it's difficult, we have little to no coverage, and we basically can see a section, a disk of the Earth. We cannot see the whole Earth. But we do get very frequent updates. So we started with 30 minutes in the first generation, the second generation gave us 15 minutes, and now the third generation will give us every 10 minutes a whole view of the Earth. And this is what it looks like if you patch this together. You get some nice loops, some nice videos. You can already see things. You can see how over Africa you have thunderstorms developing. You have some systems coming in the North Atlantic or in the South. And that's already something you can work with. Now, I said we have one satellite that can look at a certain thing. Now, if you have some multiple satellites, in this case 5, you can do something which we call as a geo-ring. So we have 5 satellites in orbit. There's more, but we use these 5. 2 American, 2 from us, 1 from Japan, and we can create this image. So I think it's like every hour, every half an hour now, we can create a global image of the Earth. And we can do a lot of science with that. We can go back in time, we will do this as well. And we can do science analysis on the whole Earth. Again, we're missing the polar areas, even with this combination. But we'll come to them. This is how satellites look. The first 2 of us, which is called MFG and MSG, standing for first and second generation, they look a little bit like a washing machine. And that's what they do, they turn. They just have a very expensive instrument inside instead of dirty washing. The next one doesn't turn anymore, but then we've got 2 of them. We've got American satellites, GOES 12 and GOES 8, and this GOES 8 I like because it has this huge antenna. I have no clue what it's for. But it was featured in the original Twister film for about 1.5 seconds. So that's why it's here. Okay, the second orbit is a LEO orbit. It's not an animal, but it's a low Earth orbit, so it's only 800 kilometers high. And this orbit now takes 100 minutes, not 24 hours. And in this 100 minutes, it goes from one pole down to another pole and comes up again. And in this time, as you can see on this little animation, the Earth turns underneath the satellite. So we don't maneuver the satellite around to get different parts of the Earth. We let the Earth do the job. We just fly the same loop all over again. And that way we can actually monitor the Earth, the whole Earth with one satellite, although the frequency is very low. You can see it comes down during sunlight, daylight, and it goes up, if you want, on the night side. So basically we have 2 overpasses per day with one satellite. Now, of course, we can have more satellites. We have at least 2. The Americans have 1 or 2. So we do get a higher frequency, but again, it's limited in the amount of, or the revisits with one satellite. The good thing is here what's called sun synchronous. So it means that whenever a satellite comes over a place, it's at the same local sun time. So it's always the same illumination situation whenever the satellite passes over. Again here, a couple of models. Ours is the METOP. We have this nice doggy house called Sentinel-6. Looks good. Apparently that was the best way to do this. This measures the wave height, or the ocean height. And then we have a Sentinel-3 and a NOAA satellite. So the second part of the physics lecture is about the electromagnetic spectrum. What you see here is the electromagnetic spectrum, and the blown up part, which is only a tiny fraction of it, is what we can see. This is visible to us, visible light, going from around 400 nanometers to 700 nanometers, from the violet to the infrared or red, and beyond that it goes to the infrared and shorter wavelengths, ultraviolet, which you might have heard in connection with ozone hole and stuff like that. But that's not all we have. We have the infrared, which is emission of the Earth. So any body that has a temperature emits radiation. We all do, the Earth does. You might have seen some images from houses or so where they're good or bad insulated. But it goes even further. We have microwave images, radio waves, and stuff like that. So this is just to show you we are measuring in different areas of this electromagnetic spectrum, and we can measure different features as we do so. And this is the example of one of the satellite instruments. It measures in these channels, these numbers down at the bottom. And you have on the left-hand side, you have the incoming radiation from the sun. And then you see these gray areas at the bottom. And that's where the atmosphere absorbs the radiation that comes in. It absorbs and it reflects. So down the ultraviolet on the right, on the left, it doesn't get to the surface of the Earth. And that's good because it's not good for us. We get sunburn, skin cancer, or whatever. So we have the ozone layer that protects us from this. Then we have the major part of the solar radiation is where we actually can see. Not really a big surprise, I would say. And then you have other gray areas. This is all trace gases in the atmosphere that block out the sunlight. And then if you go further along in the spectra, this is the area where the Earth is actually emitting radiation, which we can measure with our satellites. And again, we have these gray areas. This is an area where the atmosphere is blocking the radiation. And then we have what is called the atmospheric window. This is the place where we can actually look down right to the surface of the Earth. And I will show you some images and some combination of these channels as we go along. Right, let's come to the instruments. So you've done the physics, that's good. Now I'll show you some instruments. The most important one is the imager. The imager is basically a huge camera, very expensive, and it measures in different wavelengths. As you see in the middle, there's, in this case, there are 16 different channels. And channels means a different wavelengths. We have the visible light at the top line, then it slowly goes to the infrared, and then you have these two here. This is the water vapor channel. And this what we see here. We don't see anything from the surface anymore. We see the water vapor distribution in the atmosphere, and we get the temperature of the water vapor in the height of the where it is in the atmosphere. And then we go further along in the infrared, and then we can see down to Earth again. And in this way, we can get information about the Earth, about the height of the atmosphere. And when we do this a little bit more, there's an instrument called a sounder. And this doesn't only have 16 channels, it has actually 8,600 channels. And in August, we're going to launch an instrument that has to be twice that many. And what we can do here is we can do this all together, all these different channels, and that what you have is this red line. This is a spectra. This is one measurement at one place in the Earth. And you can already see the higher the line is, the warmer it is, the further down in the atmosphere we can look. And you might see things here, cloud and surface. This is areas where we can actually look down to the surface, or we see clouds. And there's other things like H2O, this is water vapor. Then we have CO, NO2, or N2O, and other things. And if we combine this in a good way, then we can get these profiles over here. So we can get temperature and humidity profiles by looking down from the top of the atmosphere down onto the surface. Which I think is quite amazing, considering that we can actually look through the atmosphere. But if we use this instrument, we can get information from different levels of the atmosphere. And this is what it looks like if you convert this to a temperature. You see the satellite moving along, and then it sort of gives you, at every measurement, it gives you a profile. Of course, it's warmer to the surface than further up. And then if you go down from the top to the surface, you already see the differences in the different layers of the atmosphere. This is another instrument, a sounding instrument. And this is called a Global Ozone Monitoring Experiment 2. And it does measure ozone, not only, but one of the major features is ozone. And we're not really seeing a profile here, we are seeing the total ozone column. So the higher, the more red, the better. More red means more temperature, more ozone. And this is basically the ozone hole over Antarctica in different years, how it developed through a month or so, I think. And it is not really closing yet, but at least we managed to stop it growing. And with this instrument, we can measure on a regular basis how much ozone is there in the atmosphere, how much is there over Antarctica, and we can see that it's slowly closing. And we only have this ozone hole because of hairspray. So we're quite happy that that isn't growing anymore. So another instrument, microwave, and it's not what you're thinking of. Yeah. So a couple of years ago, this is what I thought was a microwave, but no, it's more something like this. This is the special sensor microwave imager and sounder, and it measures in a little arc on the footprint. And you also see on the top right here, these lines show one channel that is it's measuring at. It's got 24 channels. Every channel measures basically at a different height. So also in this area, with this instrument, we can get a profile. And the good thing is, microwave images or sounders, they can look through clouds. Clouds doesn't interest them. So we can always see the surface or high up in the atmosphere, even if there's clouds. So this instrument is very important for weather forecasts. Another thing that's very interesting is GPS. So we all use GPS to get here to the FedCon, but you can also go do the other way. What GPS does, it sends out a time signal. And if you receive several of these time signals, you can calculate where you are. But if you know where you are and you receive these time signals, you know how long it took this time signal to arrive to your place. And with that information, you can go back and calculate the distance and the track it took. And you might know if you put like a stick into water, the stick looks bent. And that is because we have a different density between air and water. And we have the same effect in the atmosphere. It's not as sharp, of course, but we do have different densities. It's higher at the surface and it's less dense in the higher up. And with this density change, also the travel of the signal from the GPS satellite changes. And again, here we can calculate temperature and humidity profiles high up in the atmosphere. So high up, there is no other measurements up there. So this is also a very important source of information. The last instrument I want to show you is a lightning imager, which is a very new instrument. Lightning occurs between the cloud and the ground. We all know this. We have something happening right here. You have lightning between clouds, you have lightning in the cloud. And all of this we can measure, we can see with this lightning imager. And I'll show you some more images later, but basically there are some very expensive cameras, very sensitive cameras that measure the light of lightning. Okay, let's go to some pretty pictures. That's what we're here for. So how do we make a pretty picture? So this is what the satellite measures. It's black and white. So if we want to get to a pretty picture, and maybe you've done some work on pictures before or know something about RGB and stuff like that. So we take 3 channels, and every channel gets one color. So instead of black and white, it's now a color. And if we put this together, we get a pretty picture in color. So easy, you know? Now, you will notice this looks a little bit different than what you may be used to. Especially these areas where we have these funny looking clouds. They are not white. they're cyan. In this case, because this is from the second generation of our Meteosat satellites, we had to cheat a little bit because we only had 2 channels in the visible, what we see, and we took the next best channel, which was a near-infrared channel at 1.6 micrometers. The drawback, or also feature, as ever you want to call it, is that at 1.6 micrometers, snow and ice crystals, they don't reflect sunlight. So effectively, snow is black. So if we would see at 1.6 micrometers, snow would be black. And that effect is here that basically we're missing the red information from these RGB triplet. So we only have the green and the blue. And that's why ice and snow has this funny color. And this already gives us some information. We can discriminate between high and low clouds. Low clouds are in white. We can see the snow on the ground. We can see high rising thunderstorms. We can see different vegetation or no vegetation. We can do a small analysis and can see where there's convective activity going on. So already with a picture like this, we can analyze the state of the atmosphere, of the weather as it is. Now, let's go into the night. Detecting fog at night is difficult. So we don't have sunlight that reflects off the fog clouds. We only have an infrared image, only a temperature image. And the problem now is fog is very low on the surface. So it basically has the same temperature as the underlying surface. So you cannot really discriminate between an open scene or a fog on the ground. So if you would have to tell me now where there's fog in this image, and there is fog, it would be difficult, I can tell you. But we can do another trick. We can use this channel up here with 3.9 micrometers, and small water droplets have a special feature. Now, as said, every body irradiates infrared radiation, but it doesn't always do or irradiates everything it could. So this is called emissivity. So if that's a number between 0 and 1. If it's at 1, you will get all the heat sort of going out. And at this wavelength, small water droplets don't. They emit only, I don't know, 50 or 60% of the possibility they could actually emit. So if we do this, we combine these infrared channels, we get a picture like this. Now, it's quite easy to see where there's fog, and that's all where there's these greenish, yellowish areas. And everything that's sort of reddish, this light red, is actually cloud-free. And if I go back, you will see it is like this area up here, Netherlands, Belgium, France, and this area down here in Spain looks very similar. But in fact, one is cloud covered, one has fog, the other one has not. So that's something we can do at night. We can also look at something like Sahara dust. We've all had it on our cars and on the streets and the windows, and it's in this image, it's in there, but you cannot really see it. So again, we use a different combination of channels, and suddenly we can see where it is. There's a huge, I mean really huge dust outbreak of the Sahara in this image, which you don't see in the normal visible. But if you combine your infrared channels correctly, you get an image like this, and we can clearly see where there's dust. And this can be used for forecast, this can be used for analysis and whatever. I like this one, not only because it's a lot of color in here. It's called air mass RGB. It does tell you about the air that's in this image. And now we're using actually the water vapor channel that is absorbing all the information coming from the Earth. So we're seeing a little bit of the humidity in the air. And all what is red is dry air. And this dry air comes from high up in the atmosphere. We've got the troposphere, where all the weather happens, and above the troposphere we have the stratosphere. There's very little exchange, so all the moisture is down in the troposphere, but sometimes there is an intrusion from the troposphere down into the from the stratosphere into the troposphere, and that's dry air, very dry air. And if it comes together with a circulation, like a low pressure system like this, you know this low pressure system will get really bad. It will intensify, you will have a huge storm. So already by looking just at this one image, you can, as a trained forecaster, you can say, this is going to be bad. On the other hand, down here, it's a bit difficult to see, but this is more in a greenish area. So this is a humid, warm air mass, which is not surprising, coming from the tropics towards Europe. Okay, let's do some time travel. We're here on the sci-fi convention, so of course we need to do something fictional as well. Well, actually it's not quite as fictional. We have TOS, so we have it as well. We have our own TOS, the original sensor. Unfortunately, people at EUMETSAT are not quite as creative or don't like it too much. They've called it MVIRI, which is Meteosat Visible and Infrared Imager. Describes it very nicely, but of course it's missing a little bit. You can compare that with a seasoned camera. You can take a picture in infrared and then visible, a little bit also sometimes also in the water vapor, but it's limited. Not that TOS was limited. TOS is great, but our TOS was limited a little bit. That's why, as in Star Trek, we got the next generation, and this is a pretty good camera now, and this is a really advanced camera. Again, people call it different SIVIRI. This is the spinning enhanced visible and infrared imager. This is the washing machine. It goes round and round in circles. That's why it's called spinning. And this was the second generation. Now, since 2.5 years, we've got to the next stage. We've got a pretty intriguing camera, I would like to call it. But unfortunately, they called it flexible combined imager. Okay, that's what we have. And but still, we can continue with Star Trek here. This is an overview, actually, of what we have had. We've had 7 in the first generation. These are different satellites with the same instrument on it. Then we have the second generation, 4 satellites, and we've just started our third generation. And of course, we can have a meeting of generations, because we're operating both in parallel. Now, this is the same scene from 2 different satellites, and you can already see the difference. So we no longer have our pretty cyan clouds. They are now white, as they should be, because we have a third channel in the visible. And this is a loop from one of the first days. It was an operation. It's pretty good. They did a pretty good job with combining the infrared now at night with the daily. And I showed it before, but you can see I like this down here. You have this it's going that way. A low pressure system just off the coast of South Africa. You have a lot of convection going on over the African continent, and we have this very, very long frontal system going from basically Europe down into the Caribbean. So this is something you can see from these satellites nowadays. And if we'll zoom in a little bit, Mediterranean, this is from the second generation. We can see our snow, we can see high clouds, and now we put on glasses. That's how I like to compare. And suddenly we see a lot more. Remember, this is from 38,000 kilometers distance. And we can now see, valleys, and we can see that the ocean is no longer black, it actually has color. And you can zoom in. This is not from the same instrument, this is from a Sentinel-3 satellite, an instrument called Olchi. And we can see ocean color, which is made up of plankton, mineral particles, and dissolved organic matter. And this is information that a marine biologist would need or would use to analyze how the state of the ocean is, or the body of water they're looking at. We can't see it from geostationary orbit so clearly, but this is the LEO orbit, so you can see there is something going on. The ocean is not black, it's not just uniform, there's something happening in there as well. This is something we can see very clearly now. There's a fire going on in Greece. This is Rhodos 2 years ago. We can see The flames, well, not quite the flames, but we can see those pixels where the fire is actually raging. They are extremely hot, so they show up in the visible and in the infrared. We can see them now, and we can see the dust or the smoke plume coming up. And we have an image now every 10 minutes for this area, and we can in future go back up. We can go to 2.5 minutes once we have the second satellite up. So this is a pretty good help also for firefighters to see where things are happening. Now, this is fog again during the daylight, but now we can see actually into the valleys of the Alps, and we can see how the fog retreats when the sun comes in. And as I said before, this is from 36,000 kilometers distance. We have a ground resolution of about 500 meters, so we can see the different valleys, we can see mountain tops and whatever. I'm pretty fascinated by seeing this. And it also helps if you can sort of have an overview of where the fog is. Right. Something else, going the other way. So no longer down at the surface, but convection. This is over Africa, and you can see how things explode and how clearly we can see what is happening. We can see the individual thunderstorms developing, but then once they are there, we can also see structures in these thunderstorms. And if you look, let's see, we can see things like here, overshooting tops. Overshooting top is something that happens in the center of a thunderstorm, where it then actually goes into the stratosphere. And areas where this happens, you will very likely have something like hail, heavy rain, storms coming down. So for forecasters, this can be a very helpful information if they see these overshooting tops, and then can do a short term, but at least some kind of warning. Okay, lightning imager, or the flashy thing. It's not this. Maybe it is and I just forgot. No, it's this one from the beginning. As I said, we have 4 high-speed cameras. We're taking not really a picture, but we're reading out the sensor every millisecond. That's quite a lot. We only read out information that is related to a flash, a lightning. And we actually already process things on board. We don't send down everything. But if we do, what do we send down is this. This is a loop of a couple of days. You see Africa again in the center, and we've got a lot of convection over South Africa, and you see loads of thunderstorms going on. We have these background images as well from the same cameras, and then we aggregate this information where there's a lightning happening, but you can also see Europe up here. There's thunderstorms in Europe, and up there in Eastern Europe even. So we have a pretty good overview of where thunderstorms are now occurring that create flashes. And I quite like this video. It starts off with a sort of normal thunderstorm here in the middle, but watch this area. There's nothing at the moment. And as it slowly starts developing, you can see there's some clouds forming, and suddenly flashes come. That looks quite impressive. I mean, this, an hour or two before, there was nothing, and suddenly this is really, there's a lot of action going on. I'm not so much into these thunderstorms, so I don't really know if that is something new. Maybe it is, but maybe not. But still, I think it's impressive to see how these things develop out of the blue. So you can imagine that people get caught in lightnings, and actually about 4,000 people per year die by lightning strikes. So this is globally maybe not a lot, but you don't want to be actually struck by lightning. This again is an animation combining the visible channel from MTG and lightning. So the red dots are lightnings, the white things are clouds, and then we have some symbols in here. These are not live observations, but these were put in later, showing where floods happened, where storms happened, where hail happened. And you can also see that this coincides with these flashes. So this is a good indicator where where things can happen, where you should be very attentive to what is happening. And you can also again see their structure in the clouds, which we can now really see some little waves where the top of the thunderstorm goes really high and sort of sends ripples through the clouds. So the big question, of course, in life is why. And you might ask yourself why we do this. Unfortunately, we don't do it for the nice, pretty pictures. I'd like to, but there is something behind it, and that's weather forecast. That's driving a lot of what we are doing. And what you see here is the development of forecast quality. So the higher up here on the left side, the higher the number, the better. And in blue, we have a 3-day forecast. So in the 1980s, the forecast was something between 70 and 90% accurate. And you see two blue lines, and the thick blue line is the northern hemisphere, and the thinner blue line is the southern hemisphere. And you see there's a big difference between north and south. And that is because in the south we have a lot less money, and we have a lot less land. A lot less money means we don't have many stations, and land means we have even less station or less land. So there's a lot less information coming from land-based observations for the weather forecast. And the other colors are different forecast range. There's 5 days, 7 days, and even 10 days. And you see that the quality has increased over the last 40 years, which is good. And you see sort of a 10-day forecast was really, really bad or just not usable. Anything below 60% is basically useless, because the easiest forecast is to say today the weather tomorrow will be the same as today, and this is right in like 60% of the time. So if you want to do a good forecast, it should be better than 60%. But you also see this gap between north and south closing quite rapidly between like the late 1990s to the early 2000s, and that's where satellites come into play. Especially the polar orbiting satellites. They measure north and south, they don't care. And this image shows you the impact of different sensors and measurement sources. So everything, the bigger the bar on the left, the better, because it's reducing the error in the weather forecast. And everything that's blue is satellite-based. So you see how important for the weather forecast satellites are. So the first three things, sources, YASI, AMSU-A. YASI is the sounder I showed you at the beginning. AMSU-A is a microwave instrument. So those alone are very, very important. And then you have winds, you have some more sounders, some more microwave data. So you see the work we're doing is contributing a lot to the weather forecast, but it's not only us. Like this CRIS is an American satellite instrument. So this is a global effort which should continue. And this is what you then get. You get either a nice map, or you get a sort of a time series. This was the forecast for today. I think it went a little bit warmer than 22 degrees. So the colleagues across the road, they're from ECMWF, they're doing forecasts not far from here. They maybe should look into the model again. But our good data is good, it's not us. It's not us. Right, what does the future bring? Well, we don't always know, but we know here for sure. We have two new missions coming up. One is MTGS, which is a METEOSAT third generation, the sounder. And then we've got METOP, the second generation, which is the polar orbiting. We have a launch on the 1st of July, so we're quite excited about that, and then in August, the next one. Just a little outlook. We have two instruments on MTGS. The S stands for sounder, so we have two sounding instruments. One is IRS, which is similar to the YASI instrument, so it's an infrared sounder that measures, it stares at different areas and measures all this huge spectra. And then we have Sentinel-4, which is measuring in the ultraviolet and visible. And IRS can cover the whole disk, but it does every half an hour. It does this upper part, which is Europe and Northern Africa, and then alternates the other areas. And Sentinel-4, unfortunately, can only do a little part over Europe. This will give us information, IRS will give us information every half an hour about the state of the atmosphere, including temperatures and humidity soundings, which I believe will be enhancing short-term weather forecasts. Like in a situation like today, you will probably increase short-term warnings a lot because you have more data, live data, rather than a radio sonde launch twice a day. So we have every half an hour data. The other one is the EPS-SG, and here again we now have 2 satellites because we have too many instruments to put it on one satellite, and it doesn't send out a beam of light or anything. This is purely illustrational purpose, except for this one there back here. This actually does send out, it's not light, it's a radar, but this is actually the only active instrument. The other ones are passive, they comes. But this one now, this is actually sending down a radar pulse and comes back, and you can get wave heights and wind speed and things like that. So we've got more instruments, we've got enhanced instruments next generation, and this is pretty exciting also to see these things happening. And well, as the first launch was like that, you get a second one. This is basically the same launch as at the beginning, but it's taken from space. So the American satellites, they have a feature of looking at a very small area every 30 seconds or so, and they knew when our launch was and where it was in South America and French Guiana and Kourou. And they pointed their satellite there, and they took these pictures, and you can actually see the rocket. This is a light red dot going through this box. That's the rocket going through, and then you have these white, this is the exhaust plumes that's sort of distributed by the wind. So I quite like that. I think it's pretty cool to see a rocket launch from a different satellite from space. And this is not purpose-made, this is a weather satellite. Okay, here is a couple of links to EUMETSAT. Took some information from Wikipedia, NOAA, Copernicus, which does the Sentinel stuff, EUMETRAIN, some images. Windy is a private company that produces weather forecasts. ECMWF, they are just across the road actually running one of the best weather models. DWD, UK Met Office as well. And yeah, come and meet us. We're upstairs. I don't know what the situation is there now, but probably tomorrow will be dry again. Then we have Andy. He's had a talk today about how to die in space, or how space can kill you. Don't know if you were there. I found it pretty scary when he showed it to us, but it was good. So if you want to learn more about this, come up and talk with us. He's also got another one tomorrow at 12. And Alan, who's sitting down there, trying to not be here, he's giving a talk tomorrow about how we actually get the data that is collected up in space down to Earth. And that's all. So thank you for your attention.